welcome to this brief course about data engineering, and also good afternoon. And we are going to speak about some basic course over the concept of data engineering, and we start, let's say, from data sources until we will speak about privacy. And I am Simone, and currently I'm working as a senior data engineer in DHL and data analytics. And I am from Italy. I was born in Milan, and now I'm living in Genoa, a bit at the south. And I have 5 years experience in data engineer. I previously worked in Vodafone, and right now since 1 year and a half in DHL. As you can see in my picture, I like hiking, I play football, and I like reading books and manga. And my other colleague is Fabio.
Yeah, hello everyone. So, like Simone, I work for DHL and I have more or less the same experience because I'm working in data engineering field like since 2029. So I live in Italy, and today we will see together with Simone the best practices and for data processing. So I hope that you will enjoy the course, and let's see if we can give you a good overview of everything regarding the data engineering world.
Yeah, exactly. Let's not be too much bored, I hope. We will start with a brief overview about data engineering in the past years and what is our responsibility in a company. And we'll proceed to data sources, the formats, how we process this data. So collecting the available tools right now in the data engineer world and how we see the data. Once we have that, we just need now to orchestrate this pipeline. We're going to show you other 2 tools for doing that. And finally, let's say that we are going to have a little sample data architecture. After that, Fabio is going to take care about scalability, in particular to the infrastructure and to the code. And we're going to speak about the cloud provider like Google or Amazon. And the last 3 topics, we are going to speak about the governance of the data, the quality, data privacy, how we want to catalog this data, so about data catalog and data lineage. So let's start with the evolution of the role and especially what we are and what we do. Fundamentally, we are developers, particularly focus on design, build, maintain system for collecting, storing, and analyzing the data. That's fundamentally, it's our focus, and we are responsible for, fundamentally, we are the guy that you speak when you need some data, when you need to understand the data, when you need to collect them, and if there are some data quality issue, generally we are the responsible one. So our responsible exactly is building this system, monitoring, maintain the data accuracy reliability, and also we are together with the platform team, we are responsible for setting up the data architecture design. So for choosing the tool of the data platform. What we want to achieve is that our data platform is scalable. So if the data grows, we don't have any problem. It's fundamentally seamless. We just need to let's say, increase the machine. And also our pipeline may be consistent and reliable. Another 2 really important topic is the monitoring and the logging, because from monitoring, we can build dashboard for data quality, and also we notice immediately if something is wrong, and we can face the issue immediately and not, let's say, forget it and notice 1 month later. And at the end, we are responsible for the optimization. Generally, these ETL are, let's say, expensive, especially if the data are big. So fundamentally, let's not say in our free time, we should, let's say, optimize the processing solution and try to improve the cost efficiency. This is generally what we do now, but in the 80s, when, let's say, the data started to appear around the company, it was exactly not like that. The first data warehouse were built by Teradata, IBM, Oracle. and they were super expensive. They were super expensive for a series of reasons. First one, it was the hardware. It was specialized hardware, so not generic personal machine bound together. So you need special skills, you need special people from Teradata IBM that was setting up the actual machine in your building. And of course, you needed the skills, to use this system. And that was not enough. In the start of 2000s, the web appeared. And as you know, I think everyone knows, the data it will just grow exponentially so soon that you don't have the time to build other data warehousing. It was just impossible to match up, the writing of the data that was increasing. And Google, of course, it was not Google, it was the first one facing this challenge because it was a search engine. So it was responsible for crawling, and with crawling, I mean analyzing all the pages that was at the time also now in the website and try to analyze them in order to make our search engine works. It was fundamentally unsustainable with data warehousing. And so they come up with MapReduce in a new programming model, and especially with the Google Cloud Storage that became Apache Hadoop. That was an open source system. The core idea was to use simple machine, like personal computer, but thousands of them. Let's say put them together with a distributed file system in order to coordinate the files saved and manage them and run MapReduce against these servers. So you fundamentally overcome the issue of specialized hardware and you unbound computing and storage. You have a machine for storage and machine for computing. We move let's say, to last 10 years. And of course, given this experience that Google had, it came up with Google Cloud Platform, also Amazon joined the market, and also Microsoft. So there is this proliferation of cloud computing, and also many projects of migration for the old on-prem system, because all the other companies, they were owning their server. But of course, they were not so good at doing that like Google or Amazon. So the last 10 years, we just moved many data engineers involved in this project on migrating the code to the Google Cloud, to the cloud environments. We have Apache Spark, that it's a new framework for distributing computing, and it's going to replace MapReduce, and it's focused on real-time data processing, and also you have machine learning integration with Apache Spark, and also over the data lake. And in the last 15 years, data security and privacy became fundamentally crucial because everyone get aware that this big company, they own our data, what they do with that. We must have some regulatory system in order to control it, like GDPR in Europe or other, let's say, political entity, for example, in Asia or in America. And what is going to expect in the future, for sure, data security and privacy will grow and grow because now with these LLM models and the AI that is, let's see, it became almost a buzzword, but security concern and data privacy becomes much and much important. There is a new architecture that is going to combine the best of the data lakes and the data warehousing, because of course, everything is not perfect. The data warehousing are still there, are still real, and they are pretty good. Let's think Oracle database, they're used everywhere. And data lakes was solving an issue, but came up with another one. The lakehouse architecture is going to combine, let's say, the best of the data lakes and the data warehousing. So right now, the data engineer, fundamentally, its main responsibility in a data-driven company, it's create a unique source of truth. What we want to do is create a data lake, a place where the data from different, let's say, business unit of the organization come in place in one system so that we make analytics of it. We can mix up the data, try to create, let's say, a bound to make decision, and to try to extrapolate information. So the first thing that the company tried to do now is consolidate their data. And also, I mean, we are not alone, no, we don't do on our own. We work closely with data scientists to understand their needs of data, potential data quality. And we work with business, and we work also with the data sources, because I think one of the key role of data engineering is understanding the data sources and the possibility issue that can come up. In fact, let's focus a bit over this topic. Fundamentally, we try to distinguish our world, that it's, let's call it, the data platform, and the external source that can come up from potential infinity source. Can be a database, can be the web, can be, I don't know, OneDrive or Google Drive. Let's focus maybe on the common source that if you work as a data engineer, you are going to encounter, that generally are SFTP server, database, queue system for streaming data, and API. SFTP is just fundamentally a server that enables the SFTP, that it's a protocol for transfer the data in an encrypted way. So that was all the point around. It's a safe place to save the data. It creates a bridge between the data platform and external sources. So fundamentally, different business units save the data in SFTP in uploads way, and we just download them and save into the data lake. It can save any format you want, from video to standard CSV. Of course, you are going to encounter a lot of database. I mean, you generally can access directly the database. They're in tabular format, or if they are, let's say, operational database, they export you the table, you can read it. Apache Kafka is a stream system. It's a queue system for fundamentally consuming the data as a JSON arable schema. We're going to speak about that. It's a data format. Generally, it's for IoT system. So fundamentally, let's speak about GPS, tracking this data in real time, or I don't know, even microservices. Fundamentally, if you work in let's say in a company where they have microservices, they're going to send you this data in this way. It's possible, and the format general JSON or Avro. And at the end, with the API, fundamentally, it's a web interfaces. It's not the application programming interfaces. And you can access fundamentally with any client you want, like Python, like Scala, Java, or Sugo. And fundamentally, it's used not to expose a service from a program generally. And you, as a data owner, you want those data from that service. You make a web request or a GET request, and you download those data. And this data generally we can be classified into three categories, mainly categories that are the structured data that generally are highly organized, and they are stored as a row and columns, and SQL database from MySQL, PostgreSQL. Now these are, let's say, really basic example where you connect database. You have the types, you have the name of the table, you have the list of the column, and you just download them. So fundamentally, the data is super clean. Generally, it's already clean. And also another example, it's Excel. This is just, let's say, a comparison that structured data doesn't mean, let's say, cleaner data. You still need to clean those data, because in Excel, as you can know, yes, you have rows and columns, but inside those rows, you can put fundamentally whatever you want. That can be a problem. And same structured data, instead, it's a second, let's say, classification. They don't represent exactly the concept of tables or row and columns, but they have tag, or generally, let's say, a key value, a pair key value. JSON, you have a key and the value associated. So if you know, let's say, the schema, the list of keys, also on HTML, you have tag. For example, you have h1 for the title. You have fundamentally a way to extract, or a way that tell you this information is placed here. So you can rebuild a table if you know the structure of this type. And finally, we have the unstructured data. that, as you can imagine, it's fundamentally pure news to this concept of schema. They come up in PDF, the images, video, even social media posts, or even logs of an application. You fundamentally don't try to apply the schema, and you treat them in a different way in order to extract the information in the best way possible. Generally, these are the most complex data being processed, and also they are generally with the biggest one in volume. But before we go in that, the main difference between structured data and semi-structured data and unstructured data is the first two ones they have in some sort of way of schema. And the schema is fundamental in the role of data engineer, and especially operating the data, because it's an agreement, so it's a protocol and a sort of contract. In fact, some people speak about data contract when they refer to the schema between the source and the data platform, and in particular the data engineer. So when, let's say, the owner of the database, the owner of the people that put you the data into the SFTP server, the way to tell you, hey, I'm gonna send you this schema, this data with this schema, and this schema generally, we can look now, it contains, I bet, it contains not the list of columns, it contains all the types, also the name of the table. In this example, we are looking at a different format schema, but generally I would say that Hub or JSON schema is the most common for 90% of the time. But let's say, for example, that this source, it does not provide you a schema, you are not able to retrieve. This is a problem because you fundamentally lose a contract between the source and the data platform. You don't know if at a certain point of time they're going to add you a table, or maybe they switch the column order. And if they switch it, for example, the value, and so the name, you don't have the schema, I mean, you are gonna find the age in the select date. And if you don't have a contract like schema, you are gonna notice this maybe in 1 month later, and maybe the business is going to notice this. So a schema is a really important concept in the data engineering world. We are gonna, let's say, focus a bit over this topic in the next two slides. Let's say it's a formal representation of the structure of the data in the data system. So generally, it contains the constraint, the data type, and the relationship.
Can it be set in any programming language?
Sorry, David?
Can it be set in any programming language?
Yeah. I would say the schema, it's a JSON. It can be defined as a JSON. So fundamentally, you can use, I don't know, generally there is Python, Scala, also Go. You can use any programming language to read and parse the schema. But I would say that generally in the big data world, the two languages are Python and Scala for parsing the data. And so you have all the libraries to already read the schema in the proper format.
Can you do this with R?
Yeah, you can do it with R, but it's, let's say, I didn't experience on R, so I wouldn't, don't know how to reply to this. Probably they have it in my experience, because I remember that it was really common to use R in a certain point of time.
See.
But my recommendation would say to go with maybe Python or some Java languages, that they, especially with Fabio. For example, what we want to do with this schema. We thanks David for the question, and for the others, don't hesitate to interrupt me for any question. Bring out. So, going a bit more in detail, what are the problem of the schema management? As I said, let's say that change the order, or maybe they add a new schema, a new column into the schema. Or maybe they change the type, from comma, so double to int, or maybe they change the column name. If they don't provide you the schema, you are going not to notice this. You fundamentally, the point is you want to enforce the schema, because if you enforce the schema, you can, let's say, be in a safe word, no? If you say, hey, I have this table is composed by these 6 fields, you are going to know for your, let's say, 1 year the pipeline runs that that table is consistent, is reliable. If you don't have the schema, you cannot do any schema enforcement, and fundamentally new possible issue of data quality will come. But of course, it's also normal that the schema can change. So what we want to know is that our table can evolve in the period of time and add new table, add new column, change the type. We are going to show to you in the next couple of slides how to, let's say, try to do schema enforcement and schema evolution. We are going to do it with Delta, and that's a really, let's say, important topic for data quality, because I think maybe people get a bit, let's say, they say, hey, now that we have the data, we can make data quality, but that's not the reality. I think the first step to come up here, because if you already have a real well documentation with your data sources, you know which data they send, how they send, in which possible issue, because I mean, their external system, no, they can have issue. And if you already know this, you're already, let's say, in a good place to have at least consistency data and reliability. Of course, data can be wrong, because for some, let's say, I don't know, maybe they send you just all the ID in the same way, but that's another discussion. So let's move instead for the unstructured data, just to complete the discussion to make the comparison. Here you don't have the schema, you have general large volume, as I was saying. And fundamentally, you renews. No, it's impossible to try to define them. And so you have 3 generally management strategies. Saving the data in data lakes, that can be in a place like a file system or a distributed file system. You save them in the raw format, and you try to extrapolate with Python libraries, even R, for example, or Java language. You extrapolate the information you need. Let's think about the PDF. No, maybe you're used to the images, but at least you extracted the text. You save in some places. It's one of, let's say, a way to try to parse unstructured data. And for example, now we are not trying to, let's say, making an LLM project. We ingest PDF and I extrapolate text, images. I do the same for PowerPoint, Word, HTML pages, and you save them in a semi-structured way in the data lake. Instead, let's say that you have logs, and or maybe even, let's say, HTML pages can be, or PDF text. You can use MongoDB, for example, as a NoSQL database. They are a special database where they store the data in a JSON-like documents, and there is a specific language for making query and try to retrieve information from the document, like give me all the document with the following, let's say, words appearing inside. Another way to do so is now with the advanced analytics. Let's say that you want to parse images, similar images you can do with some model with machine learning, or maybe some, let's say, most common document with same topic, you can do some NLP. Now that we know more or less our challenge, let's look at how do we do this data processes, how we do connect to the external source, which program we can use, and do we receive the data every day? Are we going to receive it like every day, a full table, or we are going to receive it like a day-by-day update? Is it possible that we receive duplicated data? Because yes, that happens. Or maybe you want to reprocess the data because you receive it error. So there are all these challenges that we must face. I mean, data engineering, as you can see before, it's not something new. There are already tools, and our goal now is to try to reuse as much as possible. So how many tools do we have? We have, sadly or luckily, a lot of tools for ingesting the data. This is the state of the art for 2024, the current war of the data engineer and data processing. I mean, you have fundamentally probably 35 analytics engine. And your point is, how how can I decide to use one? My recommendation, if you have a really specific use case, like I really want to have zero latency because I really need to be streaming in real time, you try to search the best tool out there. But if it is the standard, let's say, ETL or processing system, just go with the standard one because they are the safest, they are reliable, and they're going to cover you 85% of the use case that you are going to find out there. And these, in our case, in the data engineer world, there are, let's say, four tools. One, it's Apache Spark, that also it's PySpark. Those I think it's in Arno for processing the data. And you can connect fundamentally to principal source, large source of format, so you can read JSON, Excel, connect to the database, available now in Scala and Python, and also now it supports also pandas. So we're gonna have a slide also on pandas because it's, I think, the main language for data scientists. And as a data engineer, it's crucial to collaborate with them. Spark also supports streaming and batch. So fundamentally, you have really a large set of features. Apache Airflow is generally the standard for orchestrating. Right now, it's in Python. There are, I think, seamless integration with so many tools out there for monitoring, for logging. There are, for example, operator to send alert to Slack. You have dashboard, already there. You have the UI. I think you can also manage complex workflow. We are going to show also other two ways to orchestrate data just for completeness. And also instead for storing our data, we are going to use this format Delta Lake. That is new format born, I think, in 2019. And I think it's crucial right now. I think all the companies try to move into this new format because it's try, to combine the best between data warehousing and data lakes. Now, speaking about before the problem, let's say adding a column with data lake, it's also free. If you save the data in CSV or in Parquet, that's another discussion, but we are going to see, I'm going to show to you in the next slide how it works. But let's focus a bit on Spark, on Spark or Pandas. The focus is extracting data, so doing ETL. We want to retrieve raw data, so from our external source, transform, cleaning, and saving to the target system. If you see here, it's really simple, for example, to connect to a database. You can have also SQL. You have already built-in function for making aggregation. Also, you have windowing function for making streaming. And another nice feature, there is also Spark for machine learning. So let's say that you want to do some k-means or clustering. You already have some built-in function. And this built function, the point they are scalable, they are already distributed, and Spark do all of this to you under the hood. And you fundamentally, you can, let's say, don't know the basic concepts of distributing computing. Of course, scalability can be a pro, but it can become also cons because you need an infrastructure, and that infrastructure, it costs, and also it costs to ramp up, I mean, if you're using Spark to process 25 megabytes of data or even 1 gigabyte, I would say that it's not my recommendation. It's a bit an overkill to try to do so. And also there is a bit of high learning curve. If you really want to use Spark in the best performance way, I mean, you need to read distributed computing. You need to read under how Spark works and how it's managing the data. Instead, let's look at Pandas. That probably the most famous library in data science world, I would say, probably with NumPy and Matplotlib, I would say. And it's super user-friendly, super easy to learn. I would say that under 2-3 GB is super performant. I mean, no issue. It's really fast. So there is a lot of integration with other Python libraries, and there are still some cons. No, it's kind of fun. You have still scalability because if you have 25 GB and you start to exploding columns and you try to make join. Yes, maybe you started with a small data set, but the data under the hood is going to increase and probably it's going to crash at some times because the memory usage, it will be too high. There is not too much concurrency for parallel and distributed processing. But as I said, now PySpark, that is the version of Python Spark, can support all the function of Pandas. So you can take the advantages of both worlds. Now that, let's say, we have processed our data, we need to store it, and which format we are going to use it. Let's forget immediately about Apache RC. It's, let's say, it was more an Hadoop ecosystem. Now that more people, I mean, more companies are moving to object storage, to cloud providers, it's not widely supported, and it's really rare to see it around. It's more a legacy format. About JSON and CSV, if you're sending some data to a business, maybe, I don't know, some report can be a good idea, but keep in mind that they are not compressed. If you have, let's say, already 1-2 GB of file, it's really a pain to save it. And also CSV, when you have, let's say, natural text inside the column, it's really prone to errors with delimiters because maybe some people know, let's say that inside the column you have new line. If you don't try to, let's say, parse them in a correct way, the CSV is going the bottom and the schema is gonna mess it around. Avro, it's another format. It's really used also for saving the data other than the schema, and it supports schema evolution. Not so efficient with pre-dev operations, so generally it's used as a final storage. But I would say that at the end of the day, Parquet is the most common storing formats, and we're going to make this choice. It's really compressed data and almost seamless to read those compression. Generally, the ratio is 1:10. So if you have 1 GB of Parquet, it's 10 GB of CSV. More or less, it's that. Of course, there is a price to this. It's lower write performance if you have 3 MB. I mean, don't write in Parquet, just write in CSV. You always need to choose by your ecosystem, the data that you are processing, and your requirements. But Parquet has some problem, and this problem, it's about immutability. Let's say, let's be back at our problem of schema evolution. Let's say that at time 0, we saved our data with 2 columns, and we add another column in the Parquet file. When you try to read that folder, your application is going to break it up because it's not supporting, the schema. Yeah, there are some way, but generally one way is to rewrite the entire table. And as you can imagine, this is a pain if you have 1 petabyte of data. And here Apache Delta counts. You have ACID transaction, you have also schema evolution and enforcement. That was one of our need in the data sources. It's open source, so you can do migration from Google to Amazon. You are not bounded to a vendor. That's really a plus. You have a lot of metadata for data quality, so you can understand the tables. And also you have the audit, so you can understand, let's say, how many writes there are in the table, what happened to the table. It's really like combining the advantage of a classic database where you have the historical transaction, so you know what to do what. And also it provides you schema evolution easy. So let's look at this example, simple example taken from the documentation. Here now we have 2 columns and we add 1 column. This is used by Spark. And also I think Pandas supports Delta Lake, if I'm not wrong. This is our table, we save at time 0, we save into fun people, Bob and Sue. 3 and 5, we create another data and we save it in delta, no in fun table. If you write this without the merge schema, it's gonna break. It's gonna race and tell you, hey, you are writing a data with a different column. And that's really, really useful if you really want to do schema enforcement. But you can do even better because you can define the merge schema to true. And the merge schema is not, let's say, straightforward in the meaning that anything that is going to change is going to be added to the final table. But what is going to look is there are compatibility. There are a series of operation in the schema evolution permitted and one not permitted. So for example, new column, change of type, some change of type, or renaming of column are permitted operation. Other operation are forbidden, and so you have the advantage of both schema enforcement and schema update. Another really useful feature, I think, is the time travel. Let's say, in this example, that you save your table at version 0. You save it in some nums, right? So fine, our first run. You save it the second time, and of course, you are going to add it at the top. And you are going to do it in append mode. In the third round, what you are going to do is write 3 new numbers, but in override mode. Let's forget about this. It's not needed. Let's focus on override. And the version 2, it will be the compatible table. But we can read still the version 1. And this is really useful if something goes wrong with the data because they send you wrong. You can fundamentally retrieve what happened before. Also, I mean, some data scientists, they told me that was pretty good for making, let's say, comparison between the output and model because you have different versions. These are some of the 2 features that Data Lake provides you for free. And generally, we must save this data in some places. So we must have some data storage, and this data storage generally for categories. We have our object storage that our new storage came up with the cloud provider, and they store data fundamentally as a web object. So when you try to access, for example, in the Google Cloud Storage, you use an API. So it's like making a get. And this is really useful for, getting for read parallelization. It's really, really well performance. And after you have block storage, that is instead, this is ideal for low latency. Generally, database, they provide you block storage, where you spin up your own MySQL database, you have it in a block storage. In the top, you have distributed file system like Hadoop, or it was like the old Google Cloud Storage before becoming an object storage. The distributed file system at the end is just an evolution of our normal file storage that we have in our computer. Now it's like an interface that connects, let's say, all our machine distributed. And which one we will choose? This slide is taken by Google that provides you any storage in your provider. A cloud storage, it's the standard storage, and it's the object where you have the metadata, the object, so the ID, how to retrieve it, and fundamentally you can store anything you want in the cloud storage. And you have the block storage, you have the file store. So generally, most of the time for doing analytics, the object storage is used, I would say. And at the end, now that, let's say, we have our pipelines, we know the data sources, we have built our data pipelines. What we want to know is we want to orchestrate them. We don't want every time running this Python from a notebook or from our computer, with a start. We want something that maybe give us a UI, a nice UI. I don't know if... Yeah, you're right about that. And anyway, about the orchestration, our focus is to have this UI in order to automate that. We want to coordinate multiple flows, and we want also to have the monitoring, because if you have UI, you have a place to check all of them. And generally, let's say that let's speak about three main orchestrator. You have Apache Airflow, that is the standard for now. It's an open source platform for programmatic schedule and monitor complex work. It has the concept of tag. So you define tasks that are noticed, that are acyclic, and they are executed generally in a sequence way. Yes, you have also a lot of operators that are integrated with external orchard libraries. Another one is Kubernetes as an open source container for automate deploying, scaling, and managing continuous application. And also we have Daxter that it's raising up a bit. I would say it's not still matching up in the market share about Airflow, but it's raising. It's more modern. Support data pipeline, also machine learning workflow, and also it provides tests. That's really a big plus, because on Apache Airflow, it's really hard to emulate the environment. And also introduce the concept of data assets. So every pipeline is like a data assets, and you can fundamentally, you can run a pipeline after another one. So it's better to manage cross dependency in between pipelines. And let's go to the next slide. So let's look a bit at Apache Airflow. And this is an example code. As you can see, this is our UI that it's extracting, transforming, loading the data, and you can define the operator. And this is very similar to open a file in Python. You define the operators that fundamentally are referring to the entire tag, and you define this way the sequence of the operator. You can define, cron time base. You can trigger a tag if you want from the UI. You have the alerting already integrated inside the operator, so you can already send up an email if something failed. And other than bind operator, we have, for example, a Databricks operator, Dataproc operator, that is a service from Google. Now, let's say that we have all the stuff in places. Now we have our orchestrator. We have the pipelines. No, so the extraction, transformation, the load. So we have the source. So let's look at the data architecture from a big point, from an higher point of view. This is, let's say, the first architecture, the first generation. Now we have only structured data, ETL, and data warehouse.
Excuse me?
Yeah.
Can I ask something about the previous slides?
Yeah, of course.
So we are using a lot of Azure services. Is there a reason you don't talk about those, or is it just another one which can do the same?
About Apache Airflow, you mean Google, sorry.
So we are using Azure.
Yeah, Azure, the cloud of Microsoft, yeah.
So is there a reason you're not?
I think in the next slide, Fabio is going to speak about cloud and different market share. So we're going to make a big comparison between Google, Amazon, and services. But yeah, no, I just take the example for simplicity, but it was not, let's say, fake sponsorship or something like that.
No, yeah, okay. Thanks.
And no problem. And be back a bit at that architecture. Know that this is taken from a paper, the Delta Lake paper. You can search it on Google, and it was just fundamentally the first overview from first, second, and third generation. In this first, there was this ETL from structured data, and the second we added the Delta Lake, but there was still the problem that the data warehouse were in places. And so you have, it was really hard to replicate the data from data lake and send them to the data warehouse because the BI was still in places and reading from the data warehouse. Yes, we did the progress and the couple storage and computation, but really big problem about reconciliation and consistency challenge. In the third generation, what we want to achieve is that, with this data lake, the lakehouse to have a unified view. So fundamentally, you have all the data, and the BI reports can read directly in SQL from all kind of data. That just, let's say, where the data engineer will try to move, because it's really hard, especially when you have a lot of data, thousands of tables, to try to reconcile that in different systems. And you need to think a bit, this is fundamentally, it's what I said before. You try to create this abstract layer in order that different business units can read from the same source and from the same unique source of truth. Let's take this brief example about the data architecture. In this case, you have thousands, probably hundreds of them in a data lake. You have this schema repeated all over and over. You have, in this example, now we have maybe streaming and batching source. We have some Spark running over database, maybe hosted on Azure or maybe on Amazon. What you want to do is read this data. You want to clean them. Yeah, I mean, probably a question now that I learned it. Yes, let me go back. But, I mean, sometimes I miss the chat, guys, so don't, let's say, be shy. So the main difference, in this, I mean, the first difference is in the old data warehouse, you are not able to, let's say, parse a PDF in SQL. No, it's fundamentally impossible. That was the first challenge. But I mean, in the 80s, there was not the problem. In the 90s, fundamentally, you were loading the data manually to the data warehouse. But the problem was that the storage were pretty expensive. If the data was growing, you fundamentally were not able to keep it up. Let's think about the web. It was too fast. So the first thing that Google came up was to splitting the storage and the computation with the concept of MapReduce and distributed file system. So when you generally spin up a database, I mean, now you have no distributed database, but that is another discussion. But the first split was to try to have thousands of simple machines, easily extendable. Now, let's say that you had the first server, two servers, you just connect one of them and you just increase the storage. And another set of machines, of course, connected by a network system, you run your algorithm against them. That was the difference. But they were still in place, the data warehouse. So fundamentally, you were maybe having ETL for loading the data into the data lake, and other ETL to keep alive the old data warehouse system. And also there was some problem because there are two differences in data lake. Renaming a table, it's let's say renaming a column inside the table, it's a pain. You need to rewrite the entire table. Instead, in a database, that is fundamentally it's seamless, it's immediate. The goal of the third architecture is to try to introduce ACID transactions. So the good things about the database and the relational database into the data lake, and also to keep the good point of the data lake. That is, let's say, the goal of the lakehouse. So fundamentally, you don't have any more the data warehouses. You have just the lakehouse, and you have a data catalog where you access all the table that you need without having another ETL that saves the data in the data warehouse. That was the main difference. Also in data lake, for example, you don't have ACID properties. When you write into Parquet, let's say, with Apache Spark, you don't have the acidic property. And I mean, one acidic property, you try to write different schema in the different Parquet in append mode, it's going to work. You try to read, it's going to break it. And that's not nice, especially if it is weekend and you save 100 GB of file, you're going to notice on Monday. Say this by experience, it's not fun, the one that happens. And this is an example of the data architecture that we are having now with Delta. In this example, we have Databricks and Spark. You can read both batching. Generally, you load the data in raw format. So you have like a sort of backup. So if something, at a certain point, maybe in 2 months, you notice that something is wrong, you don't want to ask the data sources to, hey, resend me the data again. So you fundamentally save everything in the raw data. So you just reprocess them in case something is wrong. It's sort of, let's say, the original backup where in case something goes wrong. Yes, Alexis?
Yes, I have a question.
Yeah.
Does this data architecture have something to do with the whole software architecture?
The whole software architecture, what do you mean? Which software architecture?
Yeah, like in the way the system is built in monolithic as a single package or built in microservices where
No,
different
now I
components.
get it. No, this is more focusing on the data. No, this is focused on how you want the data flow in the system, no? Because you need to treat like the data is like a product, or you want that this data is clean. Like you don't, how the code works, you know, how do you deploy the code? How you, let's say, you make, for example, no, a new release, it's another things. It's let's say focus on more the code side. That maybe yes. I mean there is another one.
Yes, then how they impact the data architecture, how the software architecture impact the data architecture, if it happen.
I mean, generally you don't want to have, let's say, a software architecture like microservices. No, you don't want to have this. Generally, you want to have a lot of pipelines, and each pipelines represent an asset that is the data. Okay, you don't want right now. I mean, you don't want that. Let's say one microservice. It's not like exposing the data, and you call the microservice and you retrieve the data. What you want to do, it's like building a gigantic set of tables. And after it's working like a sort of microservice. Once the people from the business access the data catalog we are going to show to you, it's going to say, hey, I want this data from this table. And it's going to be served. No? And you can access that catalog in many ways. But let's say in the backend, this is like the backend of the data. What you want to know, what you want to do is filling up the data lake with data consistency. So each pipelines, let's say that live in their own, no, because each data is different. Maybe you need to trade, let's say you have different from you have data different from across the country with different unit system. You want to make homogeneous between each others, right? And so each pipeline represents the data produced by them. No, there is no, let's say, microservices in this place right now. Maybe you spoke about something like data mesh or something like that. No, data mesh is, for example, try to mix it up, let's say, apply microservices to data world. Generally, it's not so common right now. Still a new thing. Yeah. Oh, yeah, that's a good point. Yeah, you're right. The first two steps, generally, it's the first step works like a backup in case you need to reprocess everything. The second step give you the data, okay, and the third step is the analysis. So, I mean, this is, let's say, it's business level. So with aggregates, you have like aggregation, maybe you have average, you have analysis. So it's already, let's say, the business level. So yes, here in this layer, it's where fundamentally you join maybe 25 tables and you make your operation. But the first two steps are saving the raw data and filtering, cleaning. Maybe you want to deduplicate the data, no? Because in the raw data, you can receive an update for 2 days ago. You fundamentally upsert them. And so you have a cleaned and let's say place where it's like the safe place for data engineering for saving the data. No, that's more the point of this architecture.
So to summarize, basically, the first step is about storing the data in the right form.
Yeah.
In the right format. The second one is about making it accessible to the machine and then cleaning it.
Yeah, exactly. Yeah, exactly. You want to have that, perfectly Because maybe in data engineer, I mean, there is a problem about the size of the data. No, if you have 1 petabyte, you don't save one single file, you break it up. No, all this complexity is hidden in this layer. So it's the place where the engineer try to give you the best and the perfect data. Fundamentally, this is the place. And from here, instead, generally, it's the data science world, no? It's like a future store. They have like all the table that they want from different business units, fundamentally perfect data, not clean data. So it's a safe place where they can do analysis. That's the goal of the architecture. Yeah. Where are these action processes? Oh, that's a good point. I think Fabio is going to speak about that. I mean, of course, this is not living into the void. Generally, you can run this into on-prem, or you can run this on cloud. And this action, it's triggered. Yeah, my bad, I forget to put it here. Let's say that there is an orchestrator that triggers the pipelines one after another. Generally, it's this. Sorry, thanks for saying this. Data manipulation language, yeah?
Sorry,
And,
can you repeat this point? The last
yes,
one, trigger one.
yeah, for example, let's go back maybe. Sorry, I need to, okay. Forget all. I'm not able to go back. Okay, let's go back a bit here. No, exactly here in the, let's say this is the first step that you trigger. Now, this is an example, but I mean, I can show you maybe something more bigger, but maybe it's too complicated. But let's focus. No, this step, it's the first step that you see before in this slide. So you have these 3 steps are replicated here, okay? And they are triggered by, for example, in this case, by an orchestrator. So you click maybe a button, I mean, I can show to you, and you process the first ETL, no, the first application that copy the data from the raw system here. You run the second job that clean this data. Maybe an analyst, a data scientist can trigger their job and try, to do their aggregation or running the machine learning model. So it's like over the top, you need something to orchestrate this job. This one job, second job, and third job. Is it clear? Okay, my bad, yes, I'm going to maybe fix this. Will you start use Apache Spark on your personal? Yes, you can need to do it. There is the standalone way. So you can just type like PySpark. No, not this one. You can type like install PySpark on Google. It's going to open the official documentation. There is the standalone version. You use pip and you can try to play around. It's similar to Pandas, the installation, not too complicated. And of course, I mean, it's just for making practice. There is also Databricks community that is free and it gives you free PySpark to use it. That it's nice things. I use it in my college time because maybe better to use your cheap notebook at that time. And if there are no other questions, I leave the word to Fabio. And I stop share. I leave it to you, Fabio.
Yeah, thank you, Simone. Let me share the screen. So let me know if you are able to see the slides.
Yes, we are.
Okay. So if one of the first slides, Simone already mentioned that scalability is a milestone for data engineering. In fact, achieving scalability is probably one of the most important responsibility for a data engineer because, any company from the smallest one to the biggest one produces and consumes a lot of data. And we must And we as data engineer, we must be prepared to efficiently handle all this data. And basically with data scalability, we want to ensure performance. That means that our systems should handle increasing loads efficiently, but without compromising the performance. That means that we must build systems that remains responsive and available, even with heavy loads, preventing bottlenecks or even worse, downtime. This is very bad. And also scalability support company growth, because a scalable system can adapt easily to changing business demands, and also promotes innovation because the company can take new opportunities without being worried by the limitation in their data infrastructure. And this leads us to the last point, that is the reaction to the external factor, because scalability enables organization to adapt and evolve in an ever-changing world. That means that you can scale up or scale down your infrastructure and with all the resources that you need without any additional effort. And you can, in this way, you can quickly react to all the external factors. You can think, for example, about what happened during COVID. Most of the people started to buying everything online because you were not able to go outside. And so shipping companies like, for example, DHL started to have an exponential growth in the volumes of their order. And you can manage these quick changes only if you build a scalable data infrastructure. And the first step to achieve scalability is through writing scalable code. With code scalability, we refer to the ability of a code base to handle increasing amounts of data, but without requiring changes in the code base itself. And that means that when we write our code, we already should have in mind what are the best practices for a proper data handling. You must be prepared for handling a growing amount of data. And as Simone already said, the same applies also for data pipelines. And you can reach code scalability applying some best practices. And the most common are using modular code design that consists in breaking down the code into smaller independent modules that can be deployed, tested, and maintained separately. So if you imagine that you have to do a fix or a security patch or whatever to a small piece of code, if you deploy a unique block of code, you will need to redeploy everything. But if you use modular code design, you can only redeploy, update only the piece of code that you need. So this is so important. And then other two very important properties of code scalability are parallel processing and distributed computing. Parallel processing is just processing multiple tasks at the same time, and this improves performance, of course, and speed up data processing. While distributed computing is just distributing the data that must be processed across multiple nodes. And this helps us to handle large data sets in an efficient way. An example of a correct distribution is using a correct data partitioning. We will see an example in the next slide. Yeah, so talking about parallelization and distributed computing, probably Spark is the best example of how the distribution of the work happen in a scalable data system. So we start with the definition of a Spark application, that is a program that is built, of course, using Spark APIs. And the Scala application is based on the communication between two main actors that are the driver and some execution that lies on a cluster. A driver is responsible for maintaining information about the application itself and most important for distributing and scheduling work across the executors. An executor is just an instance of a Java virtual machine which physically runs the application and receive instruction from the driver. So how the work distribution works in Spark. First of all, in response to a Spark action, that is, a Spark action is when you want to retrieve the data from your dataset. So, for example, count is an action because you want to retrieve the total number of rows inside the dataset. The same is for collect, and with write, you want to physically write your dataset into a location in a proper format like CSV, delta table, and so on. So when you do an action, then the Spark driver converts your code into one or more Spark jobs. And this is the first level of work distribution. Then each job is divided into smaller set of tasks that are called stages, which are just a set of ordered steps that are needed to complete a job. And these steps are dependent on each other because the stage can be completed only if each job, the job can be completed only if each stage inside the job is completed. And finally, again, the stages are split into tasks. A task is a single unit of work, and each task maps to a single core and works on a single partition of data. So a partition of data, I've already mentioned the partitioning, and partition is just can be just seen as a slice of data. Tools like Spark divides large dataset into piece of data called partitions, and you can try to reach an even distribution of the workload by applying a proper partitioning. So let's do an example with DHL shipment data. You may think that, I don't know, using import country as partitioning column can be a good idea. But probably this is not the best solution because most of DHL shipment data is from Germany. So you will obtain a skewed distribution of the workload. You will obtain a skewed distribution partition because the partitioning that refers to German data will be much larger than all the other partition. So you can think to partition the data starting from the shipment date and then using columns like months, year, or week to properly partition the data and distribute the work across all the executors. And then we just saw that how we can process a large amount of data writing scalable code, but a full scalable environment requires that scalable code must be run on a scalable infrastructure. A scalable infrastructure is basically the ability of a network system and so on to handle a growing amount of work, and more important, to be prepared to accommodate new work. So you have to build systems that are already prepared to receive an increasing workload. And infrastructure scalability also helps to reduce costs by only utilizing resources when they are needed. So business can easily scale up or scale down as needed and consume the resources that they need and pay for what they need. And we can build a scalable infrastructure by using scalable technologies and practices. In that way, organization can build a robust system capable of supporting the growth that we were talking about. For example, you probably already know, in the latest years, most of the biggest companies started to move on the cloud, because platforms like AWS, Google Cloud, and Microsoft offer scalable infrastructure services, and that can help a company to meet their operational needs without having a fixed infrastructure. And talking about scalability of the infrastructure, also technologies like Docker and Kubernetes are crucial because they enable a scalable deployment and management of our applications. And when we do scalability, the first thing to consider is how we want to scale. There are basically two types of scalability, vertical scalability and horizontal scalability. Vertical scalability consists in increasing the capacity of an existing hardware or software by adding more resources like CPU, memory, storage. And we have some pros and some cons. The pros are that upgrading the hardware, of course, will give you best performance, and you will have also an easy management because vertical scaling usually involves the upgrade of a single node, as you can see from the picture. And this is usually less complex than scaling horizontally and managing multiple nodes. But as you have also disadvantages with this approach. For example, you have limited scalability due to the physical constraints of the hardware. For example, you can't install 20 terabytes of RAM on your personal computer because, yeah, there is a physical limitation. And one of the most weak points of vertical scalability is that in most of the case, you will have a single point of failure because having just one node or very few nodes means that if the nodes for some reason fails, then you will encounter a downtime for your system. And this is very bad because you must ensure availability in each moment. The other approach is horizontal scalability that consists in adding more instances of hardware or software to distribute the loads. And the pros are that more nodes can handle a larger number of upcoming requests, of course, and also that the loads can be distributed across multiple nodes. And also you don't have the single point of failure that you had with vertical scalability because you have multiple nodes. So if one of the single nodes for some reason fails, then you have other nodes and you can redirect all the requests to the other nodes. And as disadvantages, the main one is that having this kind of scalability means that you have to manage multiple nodes. So compared to vertical scalability, you have more complexity and you need to be more careful when you manage all this hardware and software. And yeah, another important tool that is fundamental for scalability is the containerization that is used to simplify application deployment and management. In fact, as we've seen, we are now facing with more complex and bigger infrastructure. So classical deployment method can be obsolete. And in this case, technologies like Docker and Kubernetes comes to help us. Because these technologies totally transformed the way of how we deploy our application. And the first tool is Docker. That is an open source tool that allows developers to package application with all the dependencies into standalone units called containers. Containers are basically executable packages that contains the images that we build, and images are some templates that contains, as I said, all the necessary components to run an application that are files and dependencies. And this is the typical flow on how we can build first an image and then a container. You start with this configuration file called Docker file, in which you can define all the dependencies that you need and that you want to put into your image. And you can start with a plain, yeah, David?
I was going to ask, is Java often used for this?
I mean, this is more not related to a specific programming language. This is just for, you can build an application in your in any language that you want, and then you can use these technologies to pack your application into a container, and then someone else from the other part of the world can just execute this container and run your application without the need to download external dependencies. And it's a pain when you when you have to run some program to download all the dependencies, because you can have also conflict between dependencies. And if you pack the correct dependency in your image, then it's just it's just everything is just ready to go. You just need to run the container and the application is ready to go.
So it's for interfacing mostly.
Yeah.
Thank you.
And yeah, no worries. Thank you for the question. And maybe, yeah, I can give you an example, because on Docker Hub, you can find already built images. So okay. Let's go to Docker Hub, for example. Okay, let's say that you want to run Spark on your local machine. Trust me, there is no easy to set up all the dependencies, because you will need to download Hadoop, Java, Scala, and the Spark libraries itself, and all the libraries need to be compatible to each other. The version needs to be compatible to each other. So you can, for example, search in Docker Hub for Spark image, and then you have two ways to obtain this image. You can use your command line and do docker pull plus the name of the image, that in this case is Spark, this one. And okay, as you can see, your image is downloaded. Or you can also use the Docker file of this image, and then you can build your own image, adding more dependencies, or just building this Docker file. Let me show you. Okay, this is the Docker file. And yeah, for example, in the first line, you are downloading the base image. So this is the page for your new image. And then, as you can see here, we do some command like update dependencies, install Python, and remove useless files. And then here we set the name of the user that will run the command inside the container. So let's download, for example, this. Sorry. Okay, let's download this Docker file. Okay, and let's. Okay, this is the Docker file. As you can see, is the one that we just downloaded. And you can build your image using, the build command. So Docker build plus the name that you want to give to your image. And this point is just for saying that you want to build in the current directory. Yeah, and as you can see, we downloaded everything, and also the command that you can see inside the Docker file were run, like the update, the install, and Python installation. So if everything is correct, the images should be, Spark images should be on my local machine. Yeah, and as you can see, this is the first image that we downloaded with Docker pull, and this is the image that we just built. And now, as I say, the containers are executable packages, so you can also execute the Spark shell directly from your image, and you can use the Docker run command to do it. And I'm using this option that is interactive mode. That means that you can use the terminal basically to your container. And I want to call the Spark shell inside our image. So let's see if it works. Okay. Yeah. Okay. So as you can see, in 5 minutes, I downloaded the Spark image. I ran the container that package this image, and then now I'm able to use the Spark shell without any problem. And so, as you can see, this approach remove environment inconsistencies because, yeah, all the dependencies are packed into the container, and the consent and easy scaling because with Docker, inside the Docker file, you've seen that you can easily add or remove resources dependencies as you need. So it's just adding or removing one line, and this is very, very fast. So let's move on to Kubernetes. That is basically the orchestration tool to manage Docker images, and works together with Docker to ship images, to ship and deploy images. Kubernetes automates the deployment, scaling, and management of containerized application across a cluster of nodes. And Kubernetes improve scalability because it provides effortless scalability, because developers can easily scale application in response to user demand. That means that you can add or remove resources like RAM, replicas, etc., just using this YAML file. Also, and this is so important, Kubernetes provides a solid infrastructure because Kubernetes is able to automatically restart or replace failed containers. And last but not least, Kubernetes comes with an easy configuration because, as I said, you can use this simple YAML file to define the desired state of your application, and you can also configure the commands that you want to be run. For example, at the startup of the container, you can define, as I said, the resources, and you have plenty of options. You can also define a replica that is basically a clone of your current container. And so if the first container for some reason fails, then you have the replica that can be used to redirect all the requests by the customers. So as you can see, this is a very strong and reliable architecture.
So, sorry, I have one question.
Yeah,
Can you go back to the slides?
yeah, problem.
Yeah, so about the automatic restarting or replacing of the failed containers, is there any way to do sort of like error logging? Because I can imagine if your script, so I'm really super new to this, so I don't know exactly
Yeah.
how it works, of course, but if any of your scripts fail because of a solid reason, because something is wrong maybe in the data, is there any way to get any information on that, or will your container just restart
No.
like an eternal loop? How does that work?
Okay, that's a very good question. And no, you can define, for example, one log file into your configuration files. You can use, for example, other dependencies like log4j, and then you can redirect all the logs to log4j and then to a specific file. And usually, what we do is that we use some audit platform like OpenSearch to look at these logs and see what happened, why something went wrong, if it's a resource problem, if it's a data problem. So, yeah, more or less, this is the typical approach that we use for log processing.
Perfect. Thanks.
Thank you for the question. And okay, so moving on, Yeah, in the latest year, moving to the cloud became also a popular trend in most industries. Organizations that have not yet moved to the cloud are concerned about topics like the security of their data, because they don't want to give their sensitive data to an external vendors. But on the other side, they want to have flexibility and scalability in their infrastructure. So organizations are asking most frequently what is the difference between on cloud and on-premise architecture, and what is the best for their businesses. And these are the main differences between an on-premise and an on-cloud environment. With an on-premise environment, the computing resources are physically hosted, managed inside a physical location that is managed by an organization. You have some pros and cons to this architecture. The advantages are that you have a complete control over hardware and software, because I mean, you buy your hardware and your software, so you have the total control over this hardware and software. And the same apply for security, because you are directly responsible for managing security over your data. And also with on-premise, you have a high level of customization, because of course, when you buy software and hardware, you buy them considering the current need of your organization. So they are very specific to the current need of your organization. But we have big disadvantages of this approach, because you need to invest a lot of money to buy all the hardware and software that are necessary to build an infrastructure. And also scalability is limited by the physical resources, as we saw in vertical scalability. And also maintenance is a pain, because every update, every security patch, every fix is on charge of you and your team. So you need to spend a lot of resources in terms of money and human resource to solve all the issues that can come with your infrastructure. But on the other side, you can use an on-cloud approach. And in this infrastructure, the computing resources are hosted and managed by a third-party cloud service provider. And as advantages, you have, of course, scalability, because you can easily scale up or scale down based on the demand. And for this reason, on cloud architecture is very cost effective, because adopt this pay-as-you-go model that reduce upfront costs. That means that you pay only for the resources that you consume. So if you run some software on some hardware for 1 hour, let's say, you will pay only for 1 hour. It's like renting your infrastructure. So you have very flexible cost. And another big advantage is maintenance, because maintenance updates, security patch, and so on are totally in charge of the cloud service provider. So you don't have to worry about anything. But on the other hand, with this approach, you have less direct control over infrastructure, because, as I said, it's like renting an already existing infrastructure. And also security totally relies on provider security measures. So you have to trust your cloud provider, and you become totally dependent to your cloud provider, and also to the internet connectivity, because yeah, you are on cloud, of course. And yeah, but moving on, at the end, in the latest years, a lot of companies decided to move on the clouds, because you can see cloud provide much flexibility compared than to an on-premise architecture, and also allow users to access to advanced technologies without the need to build and maintain a heavy infrastructure. because this is possible because cloud providers like AWS, Azure and GCP offers a wide set of services, and but at the end, yeah, you can choose the best provider that fits with your needs. For example, most big enterprises choose Azure because they already own some Microsoft infrastructure. So, of course, the best solution is to choose Azure. But on the other hand, AWS was the first cloud provider on the market, so some new customers are more convinced to go with AWS. But as you can see from this table at the end, the services that they provide are more or less the same, with only with a different name. For example, all the cloud providers provide Docker and Kubernetes management, but with different names. AWS called Kubernetes management Elastic Kubernetes Service. Google Cloud called the same service Kubernetes Engine, and Azure called again the same service Kubernetes Service. So it's just a matter of what you want to choose, but more or less the services are the same across all the cloud providers. Talking about the market share, as you can see from this slide, AWS is the market leader with a market share of 32%. And this can be attributed because to the name that AWS has on the cloud market, because it was the first cloud provider on the market. And at the second place, we have Azure with the 22%, and it's used by, as I said, by companies that already own some Microsoft infrastructure. And then we have at the third place Google Cloud with a market share of 11%. And this is used by a lot of telco companies or media companies. For example, Sky and Revolt are using Google, while other big companies like Netflix, Nike, and Coca-Cola are using AWS, and other companies like PayPal, Bosch, T-Mobile are on Microsoft. So you see, very big companies are already on cloud, and this, in my opinion, this will be the trend in the next years. The cloud market share will increase in the next year because yeah, you have a lot of advantages compared to an on-premise platform, and I think that we will go into that direction. Okay, now
Can I ask one question
yeah,
about
sure.
the slide with the services?
Yeah, okay, this one.
Yeah, I saw that. Oh no, sorry, the other one. I saw that Salesforce also offers a cloud service, but it is also using AWS.
No, this okay. To be honest, I'm not an expert about Salesforce, but I think that all the providers that are listed in this chart are cloud providers, and they provide their own cloud solution. For example, Alibaba is not so known in Europe because it's a Chinese cloud provider, but if you see the statistics for China, if I remember, like 80 or 90% of the Chinese company are on Alibaba Cloud or on Huawei Cloud. So it's yeah, these are basically service cloud providers. So
All right, thanks.
Yeah, no problem. So moving to another totally different topic, and that probably it's more boring, but sorry guys, but this is necessary when we're talking about data processing, and this topic is data governance. Data governance is a set of principles and processes that are used to rule data collection, management, and data use. And it's a framework that ensures that our data is managed properly through its life cycle, and to maintain its quality, security, and usability. We have some key pillars, a lot of key pillars, to be honest, in data governance. But to me, the most important ones are data ownership, that consists in assigning responsibility and ownership for a specific data asset. Then we have data quality, that ensure that the data is in any moment accurate, complete, and consistent. Then we have data security and privacy, that consists in protecting sensitive data from third-party unauthorized access. And we have also data compliance, that are basically the legal policies that we use to protect our data, like GDPR. So the first pillar is data ownership, and refers to the responsibility that is assigned to an individual or to a team for managing specific data assets inside an organization. And the most important role for a data ownership is for sure the data owner, because the data owner is the person that is responsible for the management and protection of the data as a strategic asset. And it should guarantee the quality of the data. It should guarantee the security, implementing and maintaining data security measures to protect, as I say, the data from unauthorized access and to possible data breaches. Data owner should ensure compliance. That means that our data and practices should be compliant with laws, regulation, and internal policies. And most important, data owner should also define a proper access management. That means defining who can access the data and under what conditions. For example, you can see how data ownership works into an IT department. The data owner probably will be the CEO, and our data asset will be the logs, the records, and our infrastructure. So for ensuring data quality, the CEO should ensuring integrity and availability of the data, and then he should implementing security measures to protect the data, but also all the processes to handle the data should be compliant with cybersecurity regulation and standards. And the CEO in this case should also managing access and permission for IT staff and also to external vendors. So probably external vendors in this case would have less permission than compared to an internal resource. And then, okay, the next pillar of data governance is data quality. That has a very big impact on business outcome, because data quality is crucial to obtain high quality insight. And these high quality insights are then used to make informed decisions and to develop effective strategies. Data quality can be badly influenced by various number of factors, such as data collection methods or data entry processes. For example, think if you manually add some data into a table, for sure you will have discrepancies between one person and one other person, and this can lead to some errors, and you can have very bad data quality for issues like that. And data quality has some important pillars that are accuracy, that is basically that we want to represent the real world values or events without misrepresentation. Yeah, for example, let's say that we are doing a traffic analysis of a website. You know that exists some bots that totally random do a very high number of clicks on your website, but yeah, this is not real data. This is noise, and you should remove this noise to your data before doing some insight. And to solve this problem, you can use some validation rules, like discarding data that are not in a specific threshold, for example. And another important quality of the data quality is to ensure completeness. Data should be present and without missing information, because missing information can lead to a mistake in the understanding of the customer. For example, let's say that you did a data collection through a survey, but and you require also the address of a customer to be filled, but for some reason you forgot to put the address as a required field. So I can assure you that in most of the cases, a field that is not required will be left empty, and so you will end up with incomplete data. And this is so bad. We want to avoid this kind of situation. You can solve the situation trying to see if exists another source of data in your company that refers to the same customer, for example, and see if in this other source of data you have the missing field that you need. Also, data should be up to date, because I mean, you can do good analysis on all data, and data should be consistent, because, as I said, it can be that different departments in the same organization do a different data entry, so you have discrepancies for the same data. You will end up to have two records referring to the same data, but with different naming convention, for example, and this is very, very bad, and this will affect our analysis. And we can solve this problem using some, let's say, standard data format, like naming convention, or using standard date format like year, month, and day when we input a date field, something like that. We must ensure that across different sources and across different departments, the data is inserted in the same way. And last but not least, we should ensure uniqueness of the data, because we should remove redundant data, because duplicates lead to skewed data analysis, and we can't make a valuable insight from skewed data analysis, of course. Okay, now let's talk about data compliance. That is how we ensure that data management practices are conform to the laws, regulation, and standards and policies. Data compliance involves the safeguard of personal and sensitive information through its life cycle inside our organization. And this is very important, because organization must be compliant with all the regulation to avoid legal penalties, and most important, to protect their trust to the customers. And also a good data compliance ensure that the privacy and the security of personal and sensitive data is protected, avoiding data breaches, because if you don't use compliance rules, this will increase the risk to have data breaches, and this will lead to reputational damage and loss of customer trust, as we already said. Yeah, I know this is boring, but yeah, these are the most famous compliance framework that are used in the organization to protect sensitive data. We have GDPR that is used inside the European Union to protect privacy and sensitive data, and requires that the organization should obtain consent to process personal data. And also an organization should report data breaches within 72 hours. CCPA is the same of GDPR, but for California residents. And then we have Health Insurance Portability and Accountability Act that protect medical sensitive information. And we have also Payment Card Industry Data Security Standard that protects information related to banks or credit cards to prevent fraudulent actions or data breaches. So data security and privacy works together with data compliance, and because helps to keep sensitive data safe. And this is essential to ensure that the company is protected from any legal or financial risk. Data privacy and data security work together to protect sensitive information and maintaining all the compliances that are defined. In particular, data privacy refers to the rights and regulation that rules the collection, storage, and sharing of personal information across an organization, and should ensure that personal and sensitive data is handled in compliance with laws and that the privacy is always respected. And with data privacy, you are allowed to collect only the data that is necessary for a specific purpose. And this approach is called data minimization. For example, let's say that you need the shipment information of a customer. You will need the first name, last name, and the shipper address, the city, of course. But there is no reason to ask also for the job of the customer or the age of the customer. You are not allowed to do that. And this is basically data minimization. Then we have data security that ensures that the data is accessible only to authorized users. And data security apply the best practices to protect data from breaches or theft. And data security should ensure integrity and availability of data in any moment, and should maintain customer trust and protect organization reputation, because as I said, if we have a data leak, this is so bad for the company's reputation. And data security use data anonymization techniques to ensure that individual identities remains confidential. And we talked in this slide about data breaches. Data breaches are basically some security incidents that can expose sensitive information to unauthorized parties. And companies apply some data anonymization techniques to try to mitigate or to prevent data breaches, ensuring that they are not exposed to that sensitive data are not exposed to unauthorized use. So in the next slide, we'll see some example where data anonymization techniques played a crucial role to improve data security in companies that were affected by data breach. For example, we have this first use case about Netflix, because in 2006, Netflix released a dataset as part of a competition to improve its recommendation algorithm. The dataset contained anonymized movie ratings, and Netflix tried to anonymize the dataset by removing personal information like names and contact. But after the release of the dataset, some researchers found that it was possible to re-identify the individuals that were present in the dataset by comparing Netflix anonymized dataset with other public datasets that were available on the internet, such as IMDb ratings. So to fix this issue, Netflix, of course, deleted the dataset and deleted also the competition. And then Netflix applied an anonymization technique called differential privacy, which introduced random noise into a dataset to prevent identification. So let's do a very simple example. You have this dataset with the user movie rating, and this is the initial data. You can add some noise to the column rating by adding a random number to the rating itself. So you will start with this dataset, and you will end with this other dataset with noise. so you can come back to the original data, and this prevent re-identification in most cases. Another data breach is AOL data breach that released 20 million search queries of user for research purposes, like Amazon. Also in this case, dataset was anonymized by replacing user ID with some pseudonyms like random numbers. But the release of the dataset led to the identification of individuals based on the unique search queries, because in the dataset you can see, for example, here the dataset consists in a username with the query that he or she did, and in some cases this query were very specific. So some hacker was able to track these queries and to track the original user that did the query. And in response to this breach, AOL adopted K-anonymity, that is a technique that consists in generalizing data. So we go from specific data to some ranges. For example, you can move a specific age into ranges like 22 to 21, 25, or 29 to a more general 26, 30. This is a small example. You can see we have here we have some very specific queries like hypertension care, diabetes management, and you can simply generalize this description, as you can see in this resulting data frame, in order to improve the data privacy. But this data leak was very bad for AOL because, of course, they had some issues with the trust of the customers, and also the lawsuit seeks at least $5,000 for each person whose search data was exposed to. So when you have data breaches, you have financial risks and reputational risks, and we want to avoid that. Yeah, these are other examples of data breaches that happen in the healthcare organization. Basically, some sensitive information like security number were not anonymized. So when this was discovered, then healthcare organizations started to use data masking techniques, maintaining the same pattern of the information, but masking the most of the field. For example, here we moved from this field, from this security number into this masked security number. We maintained only the last numbers, like this is what happens when you do when you use some marketplace and you pay with your credit card. The first charts are anonymized and only the last characters are shown. That's why to be compliant to security rules. And then the last case that I want to show you is Google Street View data collection in 2010. Because Google collected Wi-Fi data, including payload data from Wi-Fi networks, while capturing images for its Street View service. And as you can see, this is a very big security problem. So as a response, Google addressed the issue by deleting the collected payload and implementing stricter data anonymization techniques like tokenization. And tokenization consists in replace some field with some general strings. For example, let's say that we want to anonymize this public network name. You can just put a token like generic SSID1 and replace to the original one. So data is anonymized and you can't get back to the original SSID. As a result, Google has agreed to pay 30 million to resolve the class action. And also in this case, you can imagine that people lost some trust in Google, because this was a very big security issue. And okay, this concludes the part regarding data privacy and data security. And let's move to the last two topics of the presentation, that are data catalog and data lineage, that are also them are essential components of a robust data governance framework. In fact, by integrating these components into data governance strategies, organization can improve their decision making. But let's start talking about data catalog. That is a centralized repository that stores metadata. And Simone showed that in the one of the first slide, that you can see columns description, data types. These are metadata that are very useful for an organization, and because make it easier to discover, understand, and use the data. And with data catalog, you can also create so-called tag templates that let you tag your data assets with structured tag. For example, you can tag your data to be used as public data, or you can tag your data to be used as sensitive data. So when you open a table and you see that it's tagged as sensitive data, you already know that you must apply all the privacy, all the privacy rule and security rules to protect this sensitive data. And data quality improves data governance, because improves data quality by providing this metadata that can help to understanding the context, source, and usage of the data. Improves also data ownership, because provide a comprehensive view of data assets, data owners, and the relationship between the data. This is very important, because when you have in an organization a very big amount of data, you have a very big number of tables. Having a data catalog can help you to navigate through these tables and search only for what you want to look. And finally, data catalog improves data compliance, because you can classify data and measure how much data is appropriately tagged, and issue alerts when you detect some anomalies, like if some sensitive data was not anonymized, or if some sensitive data was not tagged as sensitive, for example. Yeah, this is an example of data catalog. This is the data catalog provided by Databricks. As you can see, we have information regarding the table, what is contained inside this table, the type of the columns. And so I think that this is a very useful tool to navigate over the data in your organization. And yeah, the last tool that we will see is the data lineage that is used to track the flow of data from its origin through its transformation and usage inside the organization, provide a clear view of how data moves and changes inside the organization. Data lineage improves data governance because improves data quality by providing visibility into data transformation, ensuring that data remains consistent, because as you can see, you can see the flow, how the data is transformed in the various steps, and how the data is transported from one table to another one. And also, data lineage is very useful because help data ownership, because as you can see, I don't know if it's visible, under each table you have the data owner. So looking at one table, you already know who is the data owner of the data itself. And also data lineage improve data compliance, because support audits of audits, because as you can see all the life cycle of each field of each table, And you can check in every moment that all the transformation that are done on a table or on a field is consistent and compliant with our policies. Yeah, so guys, that's all. So this was the last argument, and thank you for your attention. We tried to give you an overview of the basic of data engineering, starting from how data is collected, then we saw how data is processed and stored, and then we saw how data can be used for business analysis, taking in consideration privacy and security measures. Yes, I can see a question. Yeah. Yes,
Yes,
please.
just a quick one.
Yeah.
In terms of the data catalog, would this be the same as the data dictionary?
I mean, maybe I don't know. I mean, maybe Simone, you can help better in this question because I think that
Yeah, I
you
mean,
use yeah.
in data dictionary, generally, you have like, let's say, a sort of schema. I would say data catalog is a bit more extensible because you also can apply function over it. Now you can anonymize some column. You can try also to have the lineage. For example, it's famous, the Unity catalog of Databricks that now is becoming, let's say, a thing, and where you can fundamentally give permission, a set permission to some viewer. So you, for example, can access some table and the other not. This is in a data dictionary, you don't have this flexibility. And also the data catalog, it's like keeping, you can access the data. In the data catalog, you can query the data catalog and say, give me the data for this table. In a data dictionary, it's a bit more, but yeah, I think we say data dictionary can be a purpose for the data catalog. You have those info inside.
Okay, thank you.
Thanks to you.
I've also got a question.
Sure.
So is there a specific tool you use for organizing or like structuring this or viewing this data lineage, or
Yeah,
how
there
do
are
you...
there are plenty of tools. The screenshot that you saw in the slides are from Databricks that
Okay.
provides their own data lineage and data catalog tools.
Okay.
But yeah, so you have plenty of tools that you can use.
Okay, thank you.
Okay, we say no more question. Thanks you for the patience.
Yeah.
And happy that you enjoy the call.